Hello, class. So today we're gonna continue reviewing on domains of functions. So when we talk about domain describes all the possible x values that a function can take. All right. So one of the functions that we're gonna look at are polynomials, and then we also look at functions that are radical and functions that are rational. So let's start off with the easy one. So the most easiest function you can get are polynomial functions. And polynomial functions are written in this form. All right. So you can think about an example of a polynomial is, let's see, where do I put that? So you can think of f of x. If I look at the definition, it says an times x to the n plus an minus 1, x n minus 1, blah, 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 all the way to a0. And what that is all saying is that the coefficients are real numbers. The power is n, x minus 1, n minus, that's supposed to be 2, n minus 2 as positive integers. So an example could be a nice quadratic expression or a linear expression, which is x plus 2. This is a polynomial. The leading coefficient is 1, which is a real number. The power is a positive integer, which is 0. So I'm good. All right. Which is 1. So I'm good. It's a polynomial. I can look at another function, which is 3x cubed plus 4x minus 1. If I look at each of the terms and I compare with the definition, the coefficients are real, so I'm all good. The powers are positive integers, so I'm good. So this is also a polynomial. All right. 1 over square root of x plus 2x is not a polynomial because it doesn't satisfy the conditions that we've outlined for what a polynomial should look like. It should have coefficients that are real, and then the powers should be what? Should be positive integers. So when I look at the first example, I see that I have a function x squared plus 4x plus 3. Clearly, that's a polynomial. So the goal is, how do I find the domain of a polynomial? All right, there's a nice equation we can actually relate to. It's a parabola. It's a quadratic expression. So you can clearly see that every x value that you try to put in will be acceptable. It can take any values of x. So because it can take any values of x, if you look at the number line, it could pick any number from negative infinity to positive infinity. So we're going to say that the domain of this function, or the values of x that this function takes, so I'm going to use a notation x belongs to negative infinity to positive infinity. Excuse me. Or sometimes you can write it out as x belongs to all the real numbers. Okay, so this is a fact. As long as you can find a polynomial, this is going to be true for its domain. It's always going to be all real numbers if it's a polynomial. So if you see any polynomial anywhere and you're asked for its domain, it's always going to be all real numbers or from negative infinity to positive infinity. Now let's look at the next example that I have. The next example that I have is 1 over x squared plus x. So if you look at this type of function, it's got a numerator and a denominator. The numerator is a polynomial. The denominator is also a polynomial. when you have something like that where you have a numerator divided by a denominator where both of them are polynomials, we say those are called rational functions. So if you recall rational functions a over b, we said we're saying that if you have any fraction, we don't like to divide by zero because it makes it undefined. So the idea for finding the domain of rational functions is that we're going to try and figure out what x value can you place in the denominator that will make it go to zero. And if we find those, we want to take it out from the real number line, which consists from negative infinity to positive infinity. So I'm going to look towards to the denominator, and I'm going to set it equal to 0. So I have x squared plus x is equal to 0. I'm going to take advantage of my factoring skills, and I'm going to see if I can factor this. I get x plus 1 equal to 0. And since it's equal to 0, I can solve it. X is equal to 0, or x is equal to what? Negative 1. So this is telling me that if I had an input which was 0, it's going to make the denominator go to 0. We don't like that. Or if I made x equal to negative 1 and I plugged it into the function, that's going to make it equal to what? That's going to make it equal to 0. We don't like that. So we found these two inputs that makes this function undefined. So we're going to take that out from the real number line. So as a visual aid, if I place the number line, and I place negative 1 over there and 0 over there. And since we don't want it, we're going to show it off by showing an open circle. Since we don't need the 0, we're going to show it up with an open circle over there, that when we get there, we kind of skip that number and continue. So by inspection, you can clearly see that the domain, the values of x that this function can take is anything from negative infinity. When it reaches negative 1, it's going to skip it because it makes it undefined, and continue from negative 1 to 0, skip 0, and continue from 0 onwards. So we can say that the domain is x belongs to as an element from negative infinity, and we'll skip. So we show a regular parenthesis to show that you're skipping. Union means I'm connecting, and then I'm going to continue from negative 1 to 0. Union 0 to infinity. Or another slick way to write the domain is you can say x belongs to all the real numbers minus what you don't want. So we don't want 0, negative 1. So you put that in a set, which is 0 and negative 1. So either way is accepted. Okay. Now let's look at the next one. So the next one, again, I have a rational function where the top is a polynomial, the denominator is a polynomial, and my goal is to find the domain of this function over here. So again, thinking about what domain is, I'm looking for what x value that I can plug in that will make the denominator go to 0. See that when I plug in any x value in the numerator, that's acceptable. So really the problem is in the denominator. I need to figure out what x value makes that denominator equal to 0 so that I can take it out from the real number line to find what the domain of that function is. So again, I'm going to take that and set it equal to 0. So I have x squared minus 6x minus 7. I'm looking for two numbers that multiply to give me negative 7. Add will give me minus 6. So negative 7 and 1, negative 7 and 1 seems to work. And since the leading term is 1, we can easily see that this is x minus 7, x plus 1 equal to 0. So we know that x is equal to 7, or x is equal to what? -1. So if I set up the real number line, I got my -1 and I got my 7. Again, I don't want them, so I'm going to show it by an open circle. Show the second one there by an open circle. And clearly you can see that for this function, this rational function, it could take anything from -infinity, but it can accept -1. So I got to skip it. And then I can continue from -1 to 7, skip 7, and continue all the way to positive infinity. So I'm looking at these three regions. So to write your domain is x belongs to -infinity to -1 union. And again, because it's an open circle, we're using this regular parentheses to show that I can get close to it but not actually get to it. Okay? And then -1 to 7 union 7 to positive infinity. Or you can simply write as x as an element of all the real numbers, but you don't want -1 and 7. Okay, all right, let's look at another function. So the next function that I have is a radical function because I see the square root sign. So with the square root, there are certain values that it takes. So we need to consider what's going on over there. So under the radical, we expect everything to be positive so that we can evaluate it. So the way we interpret this is that we're trying to say that x squared minus x, if it has to be positive, we are saying it has to be greater than 0. The question is, can the square root evaluate 0? Yes, it can. So we also want to make it greater than or equal to 0. All right. If I can have that, then it could pick any x value that satisfies this expression over here. So again, I'm seeing things that I can factor, so I'm going to utilize my factoring skills and see if I can solve this inequality. So for those of you who've done inequalities before, you know how to solve this. Those who haven't done it, this is how you want to do it. You want to try and find the zeros of the left side. So if I pick x minus 1 equal to 0, x is equal to 0, or x minus 1 equal to 0, x is equal to 1. So I got two numbers, 0 and 1. And what I'm going to do is that I'm going to put them on the number line. I'm going to put 0 and 1. And because I'm using the inequality greater than or equal to, I'm going to show a filled in circle and a filled in circle over there. All right. And my job is to pick a number within these three intervals that I've created to see, does it satisfy the expression x minus 1 greater than or equal to 0. So if you pick a text case like x equal to 5, I get 5, 4 clearly is greater than 0. So I like this region over here. All right, I want to pick this region here. And then if I pick a number, which is -1/2 times -1/2 minus 1. Well, sorry, I'm using the wrong number. Between 0 and 1, I can pick a half. So if I pick a half, 1/2, 1/2 minus 1, that is less than or equal to 0. So it fails the test. So this I don't want. And then if I pick any number less than 0, so if I pick -5 and then -6, that is greater than what? Greater than or equal to 0. I like this region too. So it seems like for me to solve this problem, to find the domain, I only need x belongs to -infinity to 0 union. Sorry, I made a little boo-boo. So because it's the filled in circle, We don't show with a regular parenthesis, we show with a square bracket. So I have that at 0. So I want to go from negative infinity all the way, including 0, and then skip all the way till I get to 1 with a square bracket showing that I want to include that 1 too, and all the way to infinity. All right, so that becomes the domain of this function over here. All right, let's look at the next one. So the next one, I have my function, and again, it's a rational function. It's got a numerator and a denominator. The top is a polynomial. The denominator is a rational function. So in this case, what we have is, what values of x can this function take? If I plug in any x value, it looks like the numerator is fine. It could take any values, but the denominator, since it's a fraction, is there a possibility where it cannot be defined? Is that x value that makes the denominator go to 0? So again, we're going to look at that denominator, and we're going to try and see, is it greater than what? 0. In this case, since we don't want the denominator to be 0, we cannot include 0. So anytime you have a radical in the denominator and you're trying to find its domain, you want to set it just greater than 0, and not like the example that we looked over here where it was just by itself and we could include 0. So if you pick up that expression, literally you're just using what is under the radical. So I have 1 plus x is greater than 0. We're saying x is greater than negative 1. So this is fairly straightforward, because if you put it on the number line, this is negative 1. Since it's greater than, we show that with an open circle. And it says it can pick anything all the way over here. So the domain is x belongs to this regular bracket, negative 1 to what? To infinity. All right, let's look at the last example. So the last example, I still have another rational function, but this time, if we try to plug things in, we need to be very strategic about this. If you think about the inputs that are coming in, if you look at the numerator, can it pick all values of x? It's a square root. So it can only pick positive integers. And then in the denominator, when I try to find values of x that can go in, since it's in the denominator, you're also looking to find, well, it's a fraction. I can divide by 0, so I need to also figure out what x values make that denominator go to 0. So we got a two-part problem over here. We need to figure out what values of x is acceptable in the numerator and what values of x is acceptable in the denominator too. All right, and that's very different from everything that we've done. All right, so sometimes when you have a radical in the numerator, you got to be a little bit careful and not ignore it. All right, because that square root takes certain values of x. So we're going to do both. We're going to do the numerator's domain and do the denominator's domain, and then we'll kind of find where they share common x values to discover what the domain looks like. So if I pick the square root of x, since it's in the numerator, it can pick up 0. 0 is okay. So when I look at its domain, I'm looking at x greater than or equal to what? 0. So what it's saying is I am at 0, and since it's greater than or equal to, it's a filled in circle, and the direction says I'm going to the right, so I'm going this way. So I can pick up all these guys. That's fine. Anything greater than or equal to 0 is perfectly fine. And then when I look at the next equation, I'm trying to figure out what values of x make that denominator equal to 0. So in this case, it turns out to be x plus 4, x minus 1 equal to 0. All right. Did I get this right? Yep. Okay, so x could either be -4 or x is equal to 1. So I'm also going to put that on the number line. This time I have -4 and 1. And again, I don't want those, so those are open circles to show that I don't want those. So it's saying that I can take anything from -infinity. When I get to -4, I'm going to skip it. And then I'm going to continue from -4 to 1, skip 1, and then continue from 1 forever. So when I compare the two, it seems like there is a common values of x from here, from here going, and also from there going. Those are the only places where both domains share the same x values. So to put things into perspective, the domain is going to be x belongs to, so I'm starting at 0 inclusive, so open bracket 0, and then I'm going to go all the way, and I have to skip 1 even though it's okay on the other side. I'm going to skip it, so I'm going to go to 1 regular parentheses, and then now they both share everything from then onwards, so from 1 to what? 1 to infinity. All right. Okay, so I hope this was a good review on what a domain is. It's just trying to find all the values of x that the function can take. All right. And there are different types, and I've tried to kind of explain it so that you know when to address certain functions. We looked at a polynomial, we looked at a rational function, we looked at radicals, and then when we start to mix things up, how do you handle that situation? For example, the last one. Okay. All right. So I hope this was a good review on domains, and our next video will review transformations of functions, and that will be it for the review.